Welcome back to the Deep Dive. Today, we're looking at a topic that I think has a serious branding problem.
Oh, definitely.
It's usually sold as this dry, dusty branch of math, full of Greek letters and headaches.
Right.
But the source material we have today, Foundations of Basic Statistical Methods, it paints a completely different picture. It's not really about math. It's about detective work.
It really is. It's the philosophy of uncertainty. I mean, it's about how we navigate a world where we can rarely be 100% sure of anything.
Right, and the core mission of this text and our dive today is to figure out how we distinguish a genuine discovery from, well, just a coincidence.
Because our brains are wired to see patterns everywhere.
Everywhere. We see shapes in clouds, faces on toast. Statistics is the tool that tells us, hold on, don't get too excited yet.
Exactly. It's a reality check.
Yeah.
And what I love about this text is that it frames statistics as a measure of surprise.
That's such a great way to put it.
Isn't it? It's so refreshing. We're not just crunching numbers for the sake of it. We are measuring how surprised we should be by what we're seeing.
So here's the plan. We are going to unpack the logic behind this straw man argument that powers pretty much all scientific testing. We'll find out why the number 0.05 is sort of the most controversial gatekeepers in science, and we'll look at why a significant result might actually be completely useless in the real world.
And we're going to do it without getting bogged down in the calculus. We're just focusing on the logic.
Okay, let's start with that logic. The text introduces the null hypothesis, and it uses this metaphor of a straw man.
Right.
Now, usually a straw man argument is a bad thing. You're misrepresenting your opponent. But here, the text implies that science relies on it.
It does. And it's completely counterintuitive to how we operate in daily life. I mean, if you have a theory, say a new teaching method helps students learn French faster, your instinct is to prove it works.
Yet you go look for evidence that supports you.
But the statistical method says, no, stop. You don't try to prove you're right. You try to disprove that you are wrong.
So you build a dummy argument just to knock it down.
Precisely. You build a model of the world where your new teaching method does absolutely nothing, where it's no better than the old one, that boring, nothing to see here world. That's the null hypothesis.
That's your straw man.
That's your straw man. And your whole experiment is designed to, punch that straw man in the face.
I like that image. So you collect your data, and then you compare it to this straw man.
Right. You calculate something called a test statistic, and you can think of this as just a standardized score. It's a way of asking, okay, if the world really was boring, if that straw man was true, how weird is the data I just found?
And this leads us to the p-value, which I feel like the p-value is the most misunderstood concept in science.
Oh, completely. I've seen people treat it like a truth score.
Exactly. Like, oh, p is 0.01, so it's 99% likely to be true.
Which is, it's totally wrong. And the text is very firm on this. The p-value is simply a probability of your data, given the straw man.
Okay.
It's saying, if nothing was happening, the chance of getting results this extreme or more extreme is X. It's just a measure of how far out in the tail of the distribution you are.
Let's visualize that. The text talks about the bell curve. Most things happen in the big, fat middle part of the bell. That's the normal stuff.
Right. If you flip a coin 100 times, getting 50 heads is right in the middle. Getting, say, 52 heads, still pretty much in the middle, but getting 95 heads?
That's way out in the tail.
Way out. The p-value for that would be tiny. It's telling you this is incredibly surprising if the coin is fair.
So if the p-value is low enough, if the surprise is big enough, we conclude the coin probably isn't fair. We reject the straw man.
Exactly. But here's the rub, and the text spends a lot of time on this. How low is low enough?
At what point do we decide we are surprised enough to call it a discovery?
Right. The magic number.
The
sacred 0.05. In linguistics, psychology, you name it. If your p-value is less than 0.05, you pop the champagne. You're statistically significant.
You get published.
You get published. But the author is pretty cynical about this cutoff. He points out, 0.05 is just 1 in 20.
It's arbitrary, a convention.
Totally arbitrary. The text gives a great example using the significant stars that programs like R will spit out. You run a test, and if P is, say, 0.052, you get no stars, no glory.
But if it's 0.048...
you get a star. You've discovered something. But logically, those two numbers are basically the same.
They represent almost the exact same level of surprise.
Exactly. And treating one as a failure and the other as a success is just absurd. It turns this whole spectrum of evidence into a binary pass-fail switch.
The author says we should treat it as a measure of surprise, not a verdict.
Yes. Stop worshiping the stars and just look at the actual number. There's an analogy in there that really stuck with me, too, about context.
Oh, the bridge.
The collapsing bridge, yeah. He says, sure, a 0.05 risk is fine if you're arguing about Dutch prefixes. But no one in his right mind would want to cross a bridge that has a mere probability of 0.05 of collapsing.
That really drives it home, doesn't it? Significance depends entirely on the stakes.
If you're testing a medicine that could kill someone, 1 in 20 is not good enough. You might need 1 in a million.
Right. Speaking of messy things, let's talk about the shape of the data, because before you even run these tests, you have to know what normal looks like.
Yes. This is the step that, well, that novice researchers often skip. They just plug numbers into the software. But many tests, like the test, they assume your data looks like that bell curve, the normal distribution.
And reality rarely looks like a perfect bell. The text suggests using a visual tool, a QQ plot.
Sounds technical, quantile plot.
Yeah, but the description was actually quite intuitive.
It is. You basically plot your actual data against what the math expects it to look like if it were normal. And if it is normal, the dots will hug this straight diagonal line, like a zipper closing.
But if the dots start peeling away from the line,
then you have trouble. If they curve or look like a staircase, your data is misbehaving. And the text gives this fascinating linguistic example with the Dutch prefix ver.
Right, they were looking at the frequency of words starting with ver, and when they plotted them, it did not look like a bell.
Not at all. It was bimodal. It had 2 peaks, like a camel with 2 humps.
Okay, so this is where the detective work comes in. The computer just sees numbers that don't fit. But the researcher has to ask why. Why does this have 2 humps?
And the answer was beautiful. It wasn't one population of words. It was 2 different types of words disguised as one. You had the transparent ver words, where the meaning is just the sum of the parts.
Like overwrite in English. You write over something.
Perfect example. But then you have opaque words, where the prefix changes the meaning completely, like understand. You don't stand under anything.
Got it. So these 2 types of words behave differently.
Drastically. The opaque words tend to be way more frequent. They're the old core vocabulary. The transparent ones are often newer or rarer. When you mix them all together, you get that weird 2-humped camel.
But when they separated them,
the bimodal shape just disappeared. And that's such a cool example of what the author calls model criticism.
right, if they had just forced the math, they would have gotten an error or a meaningless result. But by looking at the shape, they learned something real about linguistics.
Exactly. The failure of the model revealed the structure of the language.
So we've checked our shape. Now we want to compare things. Is Group A different from Group B? The text spends a lot of time on the t-test.
The classic student's t-test. It just compares 2 averages to see if the difference is real or just, random noise. But even here, there's a trap.
The tails, again, one-tailed versus two-tailed tests. This always confuses people.
So think of it this way. You're testing a new energy drink. A 2-tailed test asks, does this drink make you faster or are slower? You're looking in both directions.
You're open to any surprise.
Exactly. But a 1-tailed test puts all its chips on one bet. Does this drink make you faster? And it completely ignores the possibility that it might make you slower.
Which the text calls risky.
It's very risky. Because if the drink actually makes people slower, which is a really important finding, a 1-tailed test that was only looking for speed will just tell you no significant result. You miss the discovery entirely.
Because you were wearing blinders.
The author argues you should almost always use a 2-tailed test. It's safer. It forces you to have a higher standard of proof, but it keeps you honest.
Let's look at the case study for the Dutch prefix on inau. They were measuring how long people pronounce the N sound. They had an old average of 0.053 seconds, and a new sample came in at 0.0498.
Now, to the human eye, those look different. You'd say, oh, the new ones are shorter.
But the data said not so fast. The p-value was around 0.13, not significant.
Right, and that's because of the variation. The data points were spread out. The text uses the idea of the confidence interval here. It's like drawing a circle around your new result that captures where the true average is likely to be.
And the old average fell right inside that circle.
It did. So the math is saying, given how messy this data is, 0.053 and 0.049 are basically indistinguishable.
But then the plot thickened. They looked at a different sound in that same prefix, the T.
And here, the assumption of normality failed. The distribution of ETH lengths wasn't a bell curve, it was skewed. So the t-test was unreliable.
You feed it garbage assumptions, you get garbage p-values out.
So the author brings in the heavy artillery, non-parametric tests, specifically the Wilcoxon-signed rank test.
The Wilcoxon sounds like a military operation.
It's a fantastic tool. Non-parametric just means it doesn't assume a bell curve. Instead of looking at the raw values, it looks at the ranks.
Ranks.
Yeah, it just lines all the data up from smallest to largest. It neutralizes those crazy outliers that can distort the average.
But the text says it has less power. That sounds bad.
It's a trade-off. You're throwing away some information, so it's harder to find a significant result. But if the Wilcoxon does find something,
You can be very confident it's real.
very confident. And in this case, it did find a real difference for the T sound, even with that messy data.
Okay, let's move on to connecting the dots. Linear regression. This is where we stop just comparing groups and start predicting things.
The realm of trends, we're trying to fit a straight line through a cloud of data points.
And they started with a very intuitive example, estimating the size and weight of objects.
Right. They gave people words like key or piano, asked for ratings. And shockingly, big things are heavy.
Stop the presses.
The correlation was massive, almost 0.99, a perfect straight line. If you tell me the size rating, I can tell you the weight rating.
But then they showed us the dark side. They plotted word frequency, singulars versus plurals. And this plot was a disaster.
It looked like a shotgun blast in the corner. Thousands of rare words clustered near zero, and then a few outliers, like the, that are used millions of times.
The regression lines hate outliers.
They're incredibly sensitive to them. It's like calculating the average wealth in a bar, and then a billionaire walks in. The average becomes meaningless.
So what do? You can't just delete them.
No, that's cheating. You use a transformation. The text champions the logarithmic transformation.
Which effectively squashes the scale.
Exactly. It reels in those massive numbers. And when they did that, the shotgun blast turned into a nice, neat oval. The outliers were tamed, and the true trend became visible.
There was a great quote here. Visual inspection of the data is mandatory. You have to look at the picture.
Always look at the scatter plot, always.
Okay, hold on to your hats because this next one, the plants versus animals study. It's fascinating.
This is where we graduate from simple lines to complex models. This is Anchovy analysis of covariance.
They were looking at familiarity versus size again. But this time, they split the nouns into plants and animals.
And when they lumped them together, the data was weird. It wasn't a straight line, it was curved. But more importantly, the cloud of points for plants was in a different spot than the cloud for animals.
Plants are generally rated smaller.
Yes, but it wasn't just that. The relationship between familiarity and size was different for each group. This is the interaction concept.
So the slope of the line depends on what you're talking about.
Precisely. The model isn't one size fits all anymore. It's dynamic. It says, tell me if it's a plant or an animal, and I'll tell you which rule book to use. It lets us quantify nuance.
Which brings us to the grand finale, the reality check. A simulation that is, frankly, a bit terrifying.
This is the most important lesson in the book, significance versus importance.
So walk us through it.
The author creates a data set of pure noise, random numbers. X has absolutely nothing to do with Y.
Scenario A, 100 random data points.
They runs a regression. The math says, nothing to see here. It correctly identifies noise as noise.
Scenario B, he ramps it up to 1,000 data points.
Yeah.
Still random noise, just more of it.
And suddenly, magic. The p-value drops below 0.05, 3 stars. The computer screams, significance.
Wait, so just by adding more junk data, the math decided it was a real discovery.
Yes. This is the trap of big data. If you have enough data, even a tiny accidental wiggle in the numbers becomes statistically significant. The math is confident the wiggle is replicable, but it doesn't know the wiggle is meaningless.
And the text proves it's meaningless by looking at the R-squared.
Right, R-squared tells you how much of the variation the model actually explains. For this significant result, the R-squared was 1%.
1%.
It explained effectively nothing. But because the sample was huge, it got the significant gold star.
So you could have a headline that says, science proves X causes Y, and they can wave a tiny p-value at you.
But if you looked at the R-squared, you'd see it explains 0.01% of the cases. It's technically true, but practically useless. The p-value opens the gate, but you have to walk in and check the other numbers to see if there's any actual treasure inside.
It brings us back to that quote, all models are wrong, but some are useful.
And we're always just trying to be less wrong than we were yesterday.
So here's a final provocative thought to leave you with. We live in a world of science says headlines. If the math can be tricked by a large sample of noise into screaming significance, how many of the breakthroughs we read about are just really, really large samples of nothing?
That's a thought that keeps me up at night. My advice: always look for the scatter plot, not just the headline.
Words to live by. Thanks for diving deep with us into the logic of statistics.
A pleasure.
See you next time.